Welcome back. In this video, we're going to look at how do we take the failure theories of fatigue and yield and apply them to a particular mechanical element. This one we're going to be talking about is springs. Now, most everybody's had some experience with springs. You played with them, you had a slinky, you've shot them across the room. There's springs in many mechanical elements, so I'm sure at some point you've interacted with them. What we're going to do in this video is take a look at how we apply our failure theories and then how we add the additional context-specific aspects that go with springs. So that's what we do for all these mechanical components, is that we figure out how our failure theories will apply, and then we take into any extra considerations based on the type of mechanical component that we're talking about. And that will be true for the ones that we cover, as well as the ones that we don't cover in this course, such as the belts and the fasteners and things. All right, so first of all, let's talk a little bit about some of the common springs you've seen. Of course, we're going to start off talking about compression springs, which are helical compression springs. These are springs, of course, that we see in lots of applications: a valve spring, the spring underneath the keys on your keyboard, and we put a force on there and we expect some deflection. We also will look at a little bit of extension springs. These usually have a hook on the end, a whole loop or two loops, and then tightly packed coils and a loop on the other end, and of course we apply the force, as the name implies, to extend that spring. And so again, the same thing applies whether we're talking about compression or extension. We put some force, we get some deflection. If you think about mouse traps, you might see a torsion spring. Anything that you want to change put force into here, like this, and cause some angle change. So we can get linear deflection, and we can get angular deflection. And that's basically the two things that we get out of most spring elements. So those are common springs that are intentionally designed as springs. You'll also see things like torsion bars, which, as the name implies, take up some of the torsion. You'll also see just long flat beams, which can be used using their material properties to also be effectively very stiff springs. So we use springs in lots of ways, and we can look at pretty much every material as a spring. That's the whole point of Hooke's law, right? Is to see things as springs. But let's discuss springs a little bit more detail, and we'll start kind of narrowing ourselves down with helical springs, and specifically helical springs drawn from round wire. So hopefully you'll have a chance to see the video that's linked for this course on the how it's made. If you search, just Google how it's made video and springs. It's very useful for kind of getting your head about how these springs are formed, which gives you some hints about a lot of the properties that we're going to see from them. So let's begin with helical compression springs. And as I said, helical compression springs are drawn from round wire, which is then formed using machines. So we'd have a round wire, and then it's twisted about, causing some helical shape. So this is my very crudely drawn spring. And of course we put our force acting against that to cause that spring to deflect. All right, so let's talk a little bit about nomenclature, just so we can be clear. If you look at a particular spring catalog, there may be some changes in the variables names that are used. A P, for example, instead of a D for diameter, but ultimately what we'll be looking at is the same types of things, but the actual letters may change. So the wire that it's extruded out of has a diameter, and that's going to be, of course, little d here. We'll call it the wire diameter. the formation of it creates a diameter, and obviously there'll be an outside diameter and an inside diameter. What's most useful for us in our nomenclature going forward is what's called the mean coil diameter. This is the diameter that's basically, if you cut a line halfway through the little diameter on each side, it will be the diameter D. So it's not exactly something that's easy to directly measure with a pair of calipers, but you can effectively do it based on the outside diameter minus the wire diameter. That will tell you the mean coil diameter. All right, the next thing that we care about is what's called N, the number of active coils. And the number of active coils and the number of coils you can actually count are not exactly the same thing. So at some point the spring has to end, and we can end it in a couple different ways. There are different what are called end conditions. So for example, if we said this was square and ground finished on the end, then the total number of coils will be the number of active coils plus 2. This is also the countable number of coils. So looking at the spring, we can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 full coils. And then how many times does this come back around? So this goes so up to here would be the beginning of the turn, and so this would be a quarter of a turn, this would be half of a turn, this would be 3/4 of a turn, and all the way back would be a full turn, right? So this is a quarter of a turn, like this, and as you can see, it is square, and we are going to assume ground and that it's finished here. But so this would be 12 and a quarter, excuse me, so that the NT of this example here would be 12.5 coils, or also called turns. So we can see that as a countable number, and what you want to do is look at table 10.1 in the Shigley textbook for all of the different end conditions. All right, so if we were to apply our failure theories and think about, will a spring fail, we're going to apply stress analysis as our first step. So we can figure out forces acting on it. It should be pretty straightforward. And now we have stress. So all springs are curved beams. So that's going to cause our stress to be a little bit different than it would be otherwise. So if you imagine just kind of cutting the spring in half here. If we had some force F, then we know that force has to be transmitted through the material. So obviously we're going to have a direct shear part. And then if this force is acting with a distance, there's going to be some torque that's caused by that d/2. So we're also going to have some torsion going on. Now, if this was just a straight beam, that'd be fine, but we also have some curvature effects in there as well. So we're going to have to approach our stress a little bit differently. So if we assumed a maximum shear stress is the product of the torsion part, Tr/J, plus the direct shear part, then we can take a look at this and do some approximation. So the T, of course, is going to be the force times the mean coil diameter divided by 2. That's why we use the mean coil diameter, by the way. The radius the radius in TR over J is going to be the wire diameter over 2, the radius of the wire. J, of course, for a round wire is pi d4 over 32. And the area of a circle is pi d squared over 4. Right. So if we take all the assumptions of a round wire, then we get this nice little formula of 8 times the force that we put on the thing times the mean coil diameter, pi d cubed, plus 4 times that force over pi d squared. So you'll notice that this has a couple different variables that change over time. Basically, the force that we put on it, typically in a design context, we know what we want to put on, what force we're going to experience, or we'll flip the problem around and say, what force can we put on this? So force doesn't change too often, but in terms of design parameters, the wire diameter and the mean coil diameter are up for grabs. Now, this makes a challenge in that we've got 2 variables in one equation, so how do we optimize for a good design for a spring? Well, it turns out we have this thing called the spring index. And I'm going to use the same as the book, which is C here for the spring index. So the spring index is the mean coil diameter over the wire diameter. Now, why this is useful is that it's a good way to characterize springs. So, for example, if we have the spring index going, say, between 4 and 12, those are pretty common values, much lower than 4, and it's very difficult to make a spring that stiff. Because it's the shape and the geometry that you're talking about becomes very difficult to manufacture. Much greater than 12, and it's typically too loose for any application that's useful. So now we're talking more like slinky level terms of spring, so it's not going to be very useful to us in a design context. So typical values for C range between the spring index range between 4 and 12. But if we set these problems with C, the spring index, you'll see that now we've got this d over d in there, which allows us to have a great simplification, and that simplification which counts for both the curvature of the beam as well as the direct shear, has a specific name. It's called the Bergstresser factor. Pardon my awful pronunciation. But it looks like this. And it allows us to apply the stress directly using the spring index. So the Bergstresser factor, KB, is 4C times, that's the spring index, plus 2 divided by 4 times C minus 3. There's also the wall factor, which is a slight correction to this, but the correction is about 1% difference. So for ease of purposes here, we'll just use the Bergstresser factor. And if you're in a particular context and you see somebody else using a different one, just log it in the back of your mind that there are other ways to go about this. Okay, so with the Bergstresser factor, that allows us to have a maximum shear stress of that factor, KB, times 8 force times the mean coil diameter divided by pi d cubed. That's, of course, for a round wire. So this corrects for the curvature and it corrects for the direct shear. So now we could go ahead, if we wanted to, and we've got shear stress, so we can, we'll have a pure shear type of case, so we can apply our yield, appropriate yield factors of safety, such as maximum shear stress theory, and we can apply our fatigue failure theories and say whether this spring is going to fail in yield or fatigue or not. Which is great, but it's not the only thing that we care about with springs. So what I want to do with the rest of this is talk about the other things that we care about with springs. So the first off is deflection. The whole point of a spring is that it causes some amount of deflection. So I'm going to skip the solution process. You can follow it in the Shigley book if you like, but basically from strain energy, what you can find is that the amount of a spring is going to deflect, a compression spring is going to deflect, of course, is related to that force. Let's say 8 force times d cubed times number of coils divided by d4 times the shear modulus of the material. And this n here is the number of active coils. So that's using Castigliano's theorem. All right, so what you see here, of course, is the geometry of the spring in the big diameters and the mean coil diameter and the wire diameter. The number of coils tells you basically geometry of the spring. And then, of course, if we're talking deflection, we need to know what material it is. We have to have a material factor in there. So if I was to move this F over here, we might see something that's a little bit more common way to describe it, which is a force of a spring that resists a spring, or it takes to deflect a spring, either way, since it's an equation mark, is some spring rate times the deflection that we want to get, or x. It doesn't matter, obviously, which one you use. So hopefully you can see that this is the same thing. We just need to solve for k. So the spring rate of a spring is the wire diameter to the fourth times the shear modulus g over 8 times the mean coil diameter times the number of active coils. So when you doing different courses and you just had a spring rate k that came from somewhere, now you can actually see where it comes from. There's geometry aspects of the spring as well as material properties. And if you don't recall from mechanics and materials, the spring modulus is related to the modulus of elasticity based on Poisson's ratio. So that's 2 plus 1 plus Poisson's ratio. And for most steels, that they're not going to change too much, about 11.5 times 10 to the 6 psi, or about 80 gigapascals for steel, which is a lot of the springs that we're going to look at. All right, so we know K. Let's think about how we actually put force onto a spring. So if we were to plot the force versus deflection y here, then if we have a K constant, then we should see something like this, right? Where we've got rise over run here is going to be a constant of K. That's our spring rate. That's what makes springs useful to us. But there's some ranges, right? So at some point, we could push on a compression spring, and it's going to go solid, right? And there'd be nothing left. So there is a point here, let's call it Y solid, where now it's basically a hollow tube that we are trying to compress. And so now, if we tried to compress that anymore, yes, it would deflect, just like all the mechanics and materials problems that you did with forces and causing deflections. But it's going to have, based on the material and the modulus of elasticity, it's going to be significantly higher than the spring rate K. Right? Now, it's also possible, we know from our failure equations, that we could put enough force on this that it's going to cause stress, and that stress is going to cause it to yield. Now, what we want to do as designers is make sure that if it yields, that point where it would yield is outside the point where it would become solid. So that we basically avoid ever getting to yield. And in the next video, we'll talk about some design principles that get us to that. But for now, this is the solid side, and then up above would be yield. Let's talk about what a spring looks like under each of these scenarios. So if we had a spring, this is Y naught. And this is our wall here. We could have a spring that would go all the way from having zero force on it, and this would be what we call our free spring length. The length of the spring when we put exactly zero force on it. So just take it out of the box and measure it. This will be L naught, the free spring length. Now, in practice, it's not useful really to ever have a spring just freely sitting there. So instead, we always keep this spring under a little bit of compression all the time. So this would be F is 0. This will be our F min, which causes some amount of deflection, our Y min. And this will be our minimum load. As you can kind of guess from this, a compression spring is going to always have a non-zero mean stress due to the fact that it's constantly operating under this minimum amount of load. So this is also called the installed length. And there are generally best practices for things like how much it should be. For example, if the spring is preset, which means that you crushed it basically and allowed some permanent plastic deformation in there, then there's some guidelines about 10 to 30% of the free length which should be used up as this Y min. And then of course we'll have some F max, which will be less than, let's say, push it here maybe, cause some max amount of deflection. Like this. So here's our F max. This will be the maximum load that we want. And you'll notice it's not the same thing as the load that makes it go solid. That's because what we want is a load that keeps it from ever hitting that solid. So go a little bit further down here, and obviously if we could have a spring, it's now basically a tube. This would be Fs, the force that takes it to go solid, and the length here would be Ls, the solid length, which is going to be a geometry factor, right? Basically the wire diameter times however many coils you have. So we want to have some crash allowance that keeps us, depending 10-20% of the length away from the crash length. So there's some principles that we'll talk about in the design principles, which are best practice rules, but not laws on how to keep that. So the maximum, that basically means that between Y min and Y max here is the working range of our spring. And our design practice is basically going to be setting up how do you find that working range and then pick a spring appropriate for the situation. All right, so that's deflection side, and then there's one more thing we need to be specifically concerned about when it comes to compression springs. If you have a real long spring and you try to push it in with your fingers, if you ever have taken apart, say, like the firing mechanisms in a firing arm, there's a nice long spring in there on automatic weapons, and if you try to squeeze it with your fingers, what obviously things that's first going to happen is it's going to bow out. That is called buckling. And one of the other concerns that we are going to care about is stability. Which is buckling. So a spring is effectively a column, and you recall from mechanics of materials that columns can buckle, and how they buckle is defined on their end conditions. So what we will look at is how to define a free length such that the spring shouldn't buckle given the force that we are under. So if you recall from Euler equation that there are free end conditions, and these we'll call alpha. They range from 0.5, 0.707, 1, and 2. And these are degrees of freedom. So 0.5 would be fixed on both ends, and 2 would be fixed free. So one end is basically completely free and allowed to rotate. Alternatively, we could have hinged, double hinged, meaning they allow 1 degree of freedom but not 2, and the fixed hinged will be the alternative. All right, so the buckling criterion is that the free length of our spring needs to be less than pi times the mean coil diameter divided by this alpha that we identified, times 2, and these are going to be material properties, elastic modulus of elasticity minus the shear modulus, and 2 times shear modulus plus E, and that's the square root of that. Free spring length is greater than this, we will not have stability. So we want to keep our free length L naught smaller than that parameter. And there are some, obviously, for particular material like steel, there's going to be a constant there. So for steel, that equation simplifies down to keeping the free length less than 2.63 times the mean coil diameter over that alpha. All right, so those are the special concerns we have for how springs can fail. We are not just concerned about yielding of fatigue stress, but we also care about whether it's going to deflect in the way that we want to and not reach solid, because again, if it reaches solid under a particular force, it can induce shock loads, which would be significantly higher energy, causing failures in other parts of our system. And we also, specifically for compression springs, are going to be caring about the stability of that spring or its likelihood to buckle. All right, so next time we're going to talk about some design principles. Until then.